Hello everybody and welcome to Thermal Physics Lesson 1. Now in this video we're going to be having a look at a few of the basic ideas and basic concepts which are really going to set us up, and obviously we're going to use again and again throughout this new topic. Firstly then, we're going to go back to the age-old idea that you guys have studied so much in the past before at GCSE and going back to Key Stage 3, both in physics and in chemistry as well, which is obviously the molecular model. Now, we know that all substances are made up of molecules, and depending on the state of matter, they're arranged and interact in different ways. Now, for a solid, we know that we have, for the molecules, a fixed arrangement. And again, you'll have heard all kinds of terms like lattice structure and all this kind of stuff to describe how they are arranged. So the individual molecules themselves cannot move position, they cannot change position, but they are still moving of their own right. They are vibrating in some way, and they'll be vibrating about some fixed position in that molecule structure, in that fixed molecule structure. Now we also know that the forces between the molecules are quite large in order to keep them in that fixed structure. When we come on to both liquids and gases then, the first thing that we know about liquids and gases is that they don't have that fixed arrangement anymore. Those molecules are free to move around. Okay, so free arrangements for both of them. Molecules are free to move. But the difference between the two is that in a liquid, the molecules are still close together, whereas in a gas, they are far apart. Finally then, when we look at the forces, well, in a liquid the forces are still there, but they're a lot smaller, a lot lower than they were when we're looking at a solid. So the forces are lower. And in fact, when we go on to a gas, they become very low. And in some ways, when we're looking at gases, we can actually take those intermolecular forces to be negligible as well. When it comes to this molecular model, though, we know, and we've been taught all the way through, that as we go to the right on this diagram, that we are increasing the temperature. What we can also see, though, from what we've looked at so far, is that at least in the green bits, in all three of them, we've got some idea of motion. So while obviously in a liquid and a gas these molecules are free to move, we can very easily measure their velocity and therefore their kinetic energy. In a solid, they're still vibrating. Well, if they're vibrating, they're still moving, and they've still therefore got some kind of kinetic energy as well. What we find then is that not only does increasing the temperature go between our three states of matter and goes from the left to right, it's also the case that we are increasing kinetic energy of the molecules as we go left to right on this diagram as well. Now again, throughout this topic, what we're going to look at, there is, as you can see, some kind of link between kinetic energy and temperature, and obviously we'll come on to that in a few videos time, but just for now, at least you understand that the kinetic energy of those molecules increases as the temperature increases, and therefore as we go up through these three states of matter. What that leads us to then is this idea of internal energy. Now we said that in any kind of substance that the molecules themselves will have a certain amount of kinetic energy. There will also, within the substance, be some form of potential energy. Now, the potential energy, depending on the substance, is going to be different and can come from quite a few different ideas of potential energy. But again, it comes due to the arrangement of it, comes down due to the electric fields, down to the magnetic fields, and all this kind of stuff going on within a material, within a substance. So there will be some form of potential energy in there as well. Now, both of these, okay, as we said, are of the molecules. So the molecules also feed in, okay, to the potential energies as well. And if we add those two together, then we end up with a measure of internal energy. Okay, in other words, the internal energy is just the sum of all the kinetic energies and potential energies that those molecules have. Okay, so internal energy is just the kinetic energy of the molecules plus the potential energy of the molecules themselves. We give that internal energy, we use the symbol U when we're looking at thermodynamics to measure internal energy and to denote internal energy. Now, it may be a different letter. You may not be used to using U for energy. You'll obviously be used to using E for energy, but we do just need to use a couple of different letters to denote what type of energy specifically in this thermodynamics topic that we care about, that we're trying to study. It is still an energy though, and therefore it will still be measured in joules as any other energy that we care about. Now again, at GCSE and even going back to Key Stage 3, you'll have come across the idea of conservation of energy quite a lot. It will have been sort of instilled into you, this idea that energy cannot be created or destroyed. It can only be transferred from one form to another. And that's obviously, at least on the macroscopic scale that we care about, that's absolutely correct. However, obviously at A-level physics, what we can do now is take it one step further and actually look at what the law itself is and draw a definition and an equation out of it. And that law then is known as the first law of thermodynamics. And there you can see on the screen the first law of thermodynamics, which states that the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. Now again, we'll sort of break this down and we'll explain it, but you can see straight away that we've got the idea in the definition of internal energy. We can therefore start to form, using this first law of thermodynamics, an equation. So let's work through it. Well, the first thing it says is that we've got the change in internal energy. So in order to denote change in, we're obviously going to use delta, and internal energy, we're going to use the symbol U that we did before. If we move on, it says is equal to, so there is the equal sign. And then what we see next is the heat added to the system. Now the idea, the symbol at least that we use for heat is a capital Q. So capital Q here denotes heat. Now, of course, we will go on in the next video to have a look in more detail about how we do measure heat and how we do quantify heat. But the basic example is, imagine if you've got some food in the oven. Obviously, we know that the oven, or at least the air in the oven, is hot and is hotter than whatever food you've just put in to the oven itself. And like a lot of things in nature, we always get a flow from high to low. In other words, the hot air, the high amount of heat that's in the air around the food in the oven, is absorbed by the colder, the cooler food that we've just put in. Just to finish off the equation then, it does say we've then got minus, and I'll explain why it's a minus sign in a moment, minus the work done by the system, and obviously we're going to use the letter W for work done again. Now, from a units point of view, again, look, we've got work done here, we know that's in joules. We've got a change in internal energy, that's in joules as well, and the heat, well again, that's just a measure of energy and is also therefore measured in joules. So everything across this equation is all measured in joules. Now, to explain the minus sign in this equation, we need to understand from both heat and work done what positive and negative for both of these mean. So let's have a look at heat first. Well, we say for the substance itself that we're studying, if Q is positive, that means that heat is being absorbed. And then obviously on the flip side of that, if Q is negative, then heat is being released by the substance. So if we're heating it up, if we're absorbing heat, Q is going to be positive in this case, and of course if Q is negative, then heat will be released, it will be cooling down. From the work done point of view, if work done is positive, then what we're saying is that work is being done by the system. Okay, so that's the key there. The work is being done by the system. Now, normally when a system does work, it is losing energy itself. Okay, so if work is being done by the system and W is positive, well, let's have a look at what happens with the equation there. Let's assume that Q is going to stay the same, that heat is going to stay the same, or we're not absorbing or releasing heat. Well, if we're doing work, okay, so if the system is doing work, then what that means is that delta U will be negative. In other words, we're losing internal energy, which makes sense from the definition of work being done by the system. Okay. Obviously on the other side of that coin, so if W is negative, then work is being done on the system. Okay, so that's why we have the negative sign in there. It simply comes from using the correct sign for W, where the work is being done by the system or work is being done on the system. Now, work being done by or on the system can come in loads of different ways, shapes and forms. If there are forces acting on the system, then work can be done on the system. If we're changing the shape or size of the system, then work is either being done by or on the system, depending on whether we're increasing or decreasing that volume and the pressures and all that kind of stuff. Again, like I said though, like with heat, and we're going to come back to heat in the next video, work done, again, we're going to come back into that idea throughout this topic and have a look at exactly what's going on with work. So hopefully a lot of that will become a lot more understandable and will start to fit together within that equation. Next then we'll have a look at temperature scales. Now there are really only two temperature scales that we need to think about and we need to worry about for this topic. Now they come in a whole raft of other temperature scales, but like I said, there are only really two that we need to care about for A-level physics. The first one you will be familiar with. It is the Celsius scale. Sometimes you'll hear that called the centigrade scale as well. Now, with all scales, you always need a couple of things to be able to define it. Firstly, you need at least 2 points, and then you will need some kind of scale division in between those 2 fixed points. For the Celsius scale then, the 2 fixed points that we use are all to do with water. It's the freezing point of water, and the other one is the boiling point of water. And then what the Celsius scale goes on to do is it goes to set the freezing point as 0 and the boiling point as 100. And that's really where the word centigrade scale comes from, because obviously cent is the French word for 100, and we've got 100 degrees in between those 2 points. Now, that might seem all well and good on the face of it, but the Celsius scale is not without its faults. Firstly, really the main thing is that it's based on a substance. It's just based on something physical rather than something fundamental. The problem with the scale is that the freezing point of water, well, it's defined as the freezing point of pure water. So in other words, if you were to try and measure exactly and precisely this temperature, this freezing point of water, you would need very specific conditions in order to do that. It's exactly the same with the boiling point. It depends also on things like the atmospheric pressure and again also the purity of the water. It all just depends on altitude and all these kinds of different things. So really it's quite a difficult scale to get measured absolutely correctly, as I said, absolutely precisely and absolutely accurately, because it's based on a substance rather than with a lot of our scales and with a lot of the constants especially that we use in physics, which are based on something more fundamental than that. What do I mean by fundamental? Well, take something like fundamental electric charge. That's based on the charge on an electron, which is a fixed number, 1.6, or minus for electron, 1.6 times 10 to the minus 19 coulombs. And that number doesn't change depending on the conditions that that electron is under at the time. It is a fundamental number. But with Celsius, water can freeze and boil and melt at slightly different temperatures depending on the conditions that that water itself is subject to. Now, the way in physics that we rectify that is that instead of using the Celsius scale, we use what's known as the Kelvin scale. Now, the Kelvin scale is very useful to us and relatively easy to understand because the scale divisions are exactly the same. In other words, a change of 1 degree C is exactly the same as the change of 1 Kelvin. In other words, if we were to take something from 20 degrees C and we were to raise it by 10 degrees C, we're also raising that temperature by 10 Kelvin as well. So that makes it relatively easy for us to understand from that point of view. The difference with the Kelvin scale comes where 0 Kelvin, not OK, that is a 0, which is known as absolute 0, is now set as the zero of the scale, and we'll discuss on the next screen what absolute zero means. Now, the value of absolute zero was determined by a physicist, a British physicist called William Thomson. William Thomson, through his work and actually through some of his political affiliations, was later made to be Baron Kelvin. Kelvin is actually named after the river in Glasgow, which goes just outside the University of Glasgow, where William Thomson did a lot of his work. So his real name was William Thomson, but he was known as Baron Kelvin, or more simply as Lord Kelvin, which is where we then derive the name of the unit from. Now, what Kelvin did, he did a lot of work on a lot of different things, but one of the piece of work that he did, he looked at the pressure of a gas as a measure of its temperature. And when he then obviously did the analysis to this, he noticed that all of them gave a straight line, but not through the standard origin that we would expect if we use the Celsius scale. Now, if you have a look on the graph, the sort of solid lines here are the measured values. Okay, so if we're using the Celsius scale, obviously this would be 0 here and increasing. What Kelvin then did, though, is he extrapolated all of these data back. And he found that if you did that, if you extrapolated these lines back, that they all met zero pressure at the same temperature, which would, on the scale, have been here. And he therefore defined this point here as absolute zero. Now, at least the way that the theory goes, absolute zero would be, for all substances, the minimum internal energy possible for a given substance. And therefore, we just, as we said, for the scale itself, we set absolute zero as 0. Now, from the Celsius point of view, that value is actually minus 273.15 degrees C. The conversion between the two scales then is extremely simple. If we're going from degrees C to Kelvin, then we would just add 273.15. And if we're going the other way around, if we're going Kelvin to degrees C, then we would just subtract 273.15. And therefore, if we use those 2 points again, so 0 degrees C would therefore be 273.15 Kelvin, and 100 degrees for the boiling point of water would just be 373.15 Kelvin. Now finally, just note that there is a slight difference. We use the degree symbol when we're talking about Celsius, but we do not use the degree symbol when we're using Kelvin. It's simply a capital K for Kelvin. So to summarise this video then, firstly we looked at internal energy, and internal energy is just the sum of all of the kinetic energies and potential energies of the molecules in a substance. Secondly, we looked at the first law of thermodynamics, and there you go. So the change in internal energy of a system, which is delta U, is equal to the heat added, so heat we use Q, minus the work done by the system. And then finally we looked at the Kelvin scale and absolute zero. So remember, absolute zero is the minimum internal energy, and we define that as 0 Kelvin. And then obviously translating that into the scale, we know that there's a difference of 273.15, so 0 Kelvin is the same as minus 273.15 degrees C. So that's it for this video. As usual, I hope you found that useful, and of course thanks for watching, and I'll see you in the next video.